In the first video, we took a look at basic IoT components that can be used for monitoring operation in remote areas. In this video, we will demonstrate different strategies for real-time monitoring of tank fill levels and pit latrine capacities, enhanced data visualizations for the IoT dashboard, as well as the scalability of the system. Let's get started by taking a look at the prototype you will be seeing in this video. At the bottom of the picture, under the table, is a reservoir tank filled with water. And in the tank is a small submersible pump which sends water up the green hose and into a top reservoir which acts as a water tank or a pit latrine for this demonstration. A valve on the top reservoir can be opened on command, which will drain the top reservoir into the bottom. Now let's take a look at the IoT dashboard and see how it can be used to visualize data from different field operations. This is the initial homepage for the dashboard website that you can connect to using a laptop or a mobile device. On the left is a map that shows 3 areas that are conducting pilots: Boston, Concord, and Wellesley. If you click on any of these areas, critical information for each site will pop up. If we click on the Wellesley site, you can see that there are 2 pilot locations linked to the area: pilot sites 1A and 1B. And once again, if you click on their locations, critical information will pop up. If we drill down a bit further, we can see that pilot site 1A is using tank, latrine, and environmental sensors in its pilot. And if we drill down even still further, we can see the actual devices with serial numbers for that location. Additional devices, pilots, areas, and even regions can easily be added, making the dashboard scalable. Now we're going to look at various ways to monitor pilot sites. Let's start with water tank monitoring. One device that can be used, which we demonstrated in the first video, is a low-raw ultrasonic sensor positioned at the top of the tank, looking downward facing the water. It's able to measure the tank fill level and send data back periodically, say hourly or once or twice a day, to the dashboard. The sensor works by emitting an ultrasonic wave towards the water, and it measures the time for the wave to reflect back and be received. The longer the time, the farther the distance. If we look back at the dashboard, we can see that pilot site 1A is red. And if we check the alarms page, we can see that the tank is at a critical fill level. If we go back and click on the sensor for that pilot site, it will bring up its real-time data. The graph shows that the fill level is about 70 millimeters high at the beginning, which is critically low, and you can see that there is not much water in the tank. So now we will turn the pump on and start filling the tank. You can see the graph rise as the tank fills from 17 to about 50 liters. Here I'll turn off the pump. If we check the alarm status now, we can see that we are notified that the water was delivered and the tank is now full. And the site is now green. Now let's drain the tank. If we go back and click on this icon in the graph, we can see the real-time data in tabular form. As it drains, the alarm status will change from full to a yellow warning status. Finally, when the tank is once again low, we are back at a critical level and alarm status. As I mentioned previously, you can connect to the dashboard with mobile devices. Here's the tank fill operation as seen on a phone. Now let's look at a different way for monitoring tank fill operations. If the ultrasonic sensor is not suited for a particular site, another way to determine fill height is to use flow meters attached to the inlet and outlet of the tank. If you know the starting fill level of the tank, in this case 0, and if you can determine how much water enters and leaves the tank, you can determine how much water is left in the tank. Here are the 2 flow meters we are using on the prototype. The inlet flow meter is a commercial grade flow meter that outputs a pulse for every gallon of water. By counting the pulses, you can determine how much water entered the tank. The bottom flow meter is actually a smaller flow meter that can be used at tap stands as well as tanks, and it works just like the other flow meter. Both meters are hooked up to a low raw sensor, which sends back flow data directed to the dashboard. So now let's look at the flow meter data by clicking on the sensor. The top graph shows the time history of the total amount of water delivered to the tank measured by the inlet flow meter. The second graph shows the time history of the amount of water dispensed through the outlet flow meter. You can see both graphs are leveled out since no water is flowing in the prototype. Now, let's turn on the pump. You can see the top graph is increasing as water is being delivered to the tank, yet the bottom graph is still level since no water is being dispensed. By the way, you can also retrieve the actual real-time data from the sensors in table form. Now we will turn off the pump and open the valve to drain the tank. You can see the top graph stays level now since no water is entering the tank, but the bottom graph is increasing, showing the water being dispensed. The dashboard can also show a top-level roll-up of operations, in this case for tank 1A. You can see the time history of fill height, daily amounts of water delivered and dispensed, as well as total amounts, environmental conditions, and a listing of the devices used at the tank site. Now, let's take a look at monitoring fill levels in pit latrines. We might be able to use the ultrasonic sensor to monitor fill height here also. However, we have noticed that some pit latrines use cement or metal lids, which would obstruct the signal sent from the sensor. Another way is to use a float switch. A float switch has a cable for the signal and a float containing a switch and a ball, as well as a weight which sets a tank depth and a pivot point for operation. When placed in a tank with a shallow fill level, the ball and the float rest against the switch, depressing it. As the fill level rises, the float rises upward and starts tilting backward. Eventually, the ball will start to roll to the other side of the float and the switch will be opened. By monitoring the status of the switch, you can determine a warning or a critical fill level in the tank. Since the cable can be routed to the outside of the tank to a low raw detector, the data signal can be sent unobstructed. This float switch is great for larger tanks, which allow for a greater range of motion of the float. However, there is another way to measure fill height for smaller tanks using two much smaller float switches. The switches can be positioned at two different depths in the tank and then are monitored once again by an exterior low raw sensor. As the level rises, the status of the float switches determine the fill height of the latrine. The two float switch method worked best for our small prototype tank. This is the dashboard for the pit latrine sensors. We can see that the status is good since the fill level in the tank is low. Now we'll turn on the pump. As the water rises, you can see the bottom float switch starting to rise, giving a warning condition. As the water rises even further, the top switch begins to rise, giving a critical condition. If we click on the pilot tab, we can once again get a roll-up of status information, but this time for the entire pilot site. You can see the latrine and tank status, water delivered and dispensed, alarms that have been raised, and the sensors used in the pilot. That concludes our demonstration. Thank you.